talked about ductility versus brittle fracture, yield strength, ultimate strength, tensile strength. And then we learned that when we have cracks, then we have to worry about crack propagation and fracture mechanics. And this was the question that was in your quiz. Of course, what I expected you to write was the equation for the stress concentration sigma m, right? So the maximum stress is related to the average stress, which was the same for all three, but the maximum depends on the flaw size, but in this case, more importantly, the curvature, the radius of curvature, and this was one way you could argue which one has the maximum stress, and it will fail sooner. And then we talked about fatigue last time, how repeated loading will make the material break at much lower strengths than, let's say, yield strengths. And now we want to talk about something very curious, and that's creep. This is a failure because of excessive deformation. What is very peculiar here is that the stress is constant. So what I mean by that, it turns out that if you have constant stress on some material, like you have a beam and you don't change anything, the stress is the same, after a while, the deformation starts to increase, even if the stress is completely constant. This phenomenon is called creep. So it starts very fast, then it has like a stable regime, and then towards the end, it becomes very fast, and then you have rupture because of excessive deformation. So we classify this as primary, secondary, and the third phase of creep. But we get to that later. This is a little bit strange because so far we didn't consider anything about time. Hooke's law doesn't tell us anything about time. The deformation is instantaneous. So if you apply a stress, you expect to have a strain right away. So what is going on here? And some other strange things also happens. For example, if you increase the temperature, the material deforms faster and breaks sooner. So it turns out that this kind of behavior we can't explain with what we know so far from Hooke's law. We have to learn about a new class of materials which gives rise to creep failure. And the failure is, if you look at the grains, it looks like you have macro cracks and then you have failure. But this happens over a long time, so it is basically time dependent. So with this introduction, let's look at the new packet. So it turns out that to be able to understand this phenomenon, we need to understand a little bit more about the mechanical properties of materials. And viscosity is the key here. Here you see a lot of pictures of asphalt because one material which is very obviously viscous and we have something to do with it in construction is asphalt. But you see that even concrete or other materials which don't look so viscous to you, they actually also have viscosity. Now, this is what I showed you already. How many recognize this building? How many have been there? What is this building? Falling White. Have you been there recently, after you've been a civil engineer? Yes. Do you remember that towards the end of the tour, if you tour the facility, they say something about the maintenance costs and how hard it is, and they talk about all these concrete beams that are cracking. So it turns out that this is, of course, a very beautiful building. Who is the architect? Exactly. It's very beautiful, as you can see. And it is famous for these cantilever beams, which stand out and become a part of the nature. But it also turns out that because it is under-reinforced, these beams, they have excessive deformation. It is old. Does anyone remember in which decade it was built?
30s?
30s, exactly. And so over time, the beams have deformed, and because of this deformation, they all crack. So this cracking due to creep is a big problem in this structure. So it has something always to do with time. And so far, we didn't know anything about time. So far, we were talking about Hooke's law. And we said that linear elastic materials, deformation is instantaneous. There is no time component. So how do we explain this time-dependent deformation? It turns out that a lot of materials, they also have some sort of a flow-like properties to them. They have some level of viscosity. And because of that, their deformation is also time-dependent. And this is what we want to learn here. Before going and talking about viscosity, I want to review a little bit elasticity. And to kind of make the comparison, we can get to that later. So one very interesting experiment is this pitch drop experiment. A professor in Australia, he wanted to show that even solid materials, they have flow-like properties. He had a lot of time, so he put a little bit of pitch, which is like it is kind of an asphalt material, into a jar, and he just waited. And his hypothesis was that even at room temperature, if you wait long enough, the solid will flow. And he was right. Look at the duration. So he started in 1927, 1930, and in 1938, finally the first drop dropped. So if you wait long enough, some materials, they flow. And then he waited longer and longer, and you see that basically the solid, which looked very solid in the beginning, actually started to flow. So most engineering materials, they are not like flows, but they are also not completely linear elastic. They are a combination, and they are called viscoelastic. So first we want to learn about viscous materials. We know about linear elastic materials. Let's review a little bit. So you have shear stress, you learned this. Shear stress, it's force divided by area parallel to it. And shear strain measures the change in shape, distortion, this angle, gamma. And if the material is linear elastic, then stress is proportional to strain. Tau is G gamma, as we can see. This is Hooke's law. What we know about linear elastic materials is that everything is time independent, and we have full recovery. We have talked about this before. If you have loading, unloading, everything goes back. If you plot a stress versus a strain, it's a straight line, and the slope is G. Now, this is kind of important. So far, we didn't talk about time. So what happens if you have a piece of linear elastic material and you apply at some point, so in the beginning there is no stress, At some point, you apply stress tau, and then you remove it. Pay attention. X-axis is time. This is something we are not used to. So far, stress versus strain. We are not used to looking at stress versus time. But imagine this is like that. Until 2:30 p.m., there is no load. Then there is a stress tau until 3:20, and then there is nothing. It's basically that. Now I want you to pay attention to how a strain changes with time. You know that a strain is proportional to a stress. This we know. So if stress is 0, then a strain would be also 0. Right? The moment I apply a stress, a strain will rise at the exact moment to the value gamma, which is tau over g. It's not any value, it is tau over g. This straight line, this jump upward, that is what, when I say instantaneous deformation, that's what it means. The moment you apply the force, the same moment you have deformation. And as long as you have the stress on, the deformation is the same. Right? The relationship is here. What happens when I remove the load? Well, it instantaneously goes down. And when it is 0, then it goes back to 0. I know this looks trivial to you, but please pay attention because these models get more and more complicated. It's important to be able to talk yourself to drawing this strain diagram. Okay, so this is how it looks like. And the stress-strain curve we have seen this always. It's a straight line, it goes back, time independent, instantaneous, full recovery. One other thing I want you to pay attention to is a model. You may have noticed that a lot of times, instead of, let's say, drawing aluminum or concrete or steel, you see, instead of that, we represent it with a simple model of a linear spring. When I say linear, it means that the force and displacement are linearly related. So this is a model for Hooke's law. Okay? It's a spring. You are familiar with it. You've seen this before. Okay. And again, the same thing. It's just repetition. So you have instantaneous deformation, then it follows, and then it goes down. These are really repeating the same thing to make sure that this is clear. Now, what happens if the material is not linear elastic? If you have a piece of caramel or honey, as a matter of fact, you apply the same force and you just wait. And you see that it's running. You have seen it probably when every time you want to put honey maybe on the toast, it just flows by itself. You don't have to do anything. You just wait a little bit. Right? It flows. So you apply the same force. If you wait, you see that the deformation becomes larger and larger. And depending on the material, if it is completely viscous, it's not going to go back. The honey doesn't, even if you put your spoon, if you take your spoon off, it's not going to take the form of the form it had before in the jar. It's completely messed up. because it's flowing. So it is very different from linear elastic materials. You have time dependent. Time becomes an important factor. Look here, 0 second, 1 second. These are, of course, cartoons. But, and there is no recovery. Look at this shape compared to where it was in the beginning. It's, of course, not the same. So it's a little bit different. So it has this flow-like motion in. The deformation becomes time dependent if the material is very viscous. And there is no recovery. What happens if you put a spoon of molasses or honey on the surface? It doesn't stay the same shape. It starts to move. Right? And it doesn't go back, even if you're not doing anything to it. So, most importantly for us, and that's what we want to learn, how do we describe this? Now Hooke's law completely falls apart. We can't use sigma equal to E epsilon anymore. This is a different kind of material. So what do we do? It turns out that people have learned about this a long time ago and have developed models to understand them as well. So one class of viscous materials follow the so-called Newton's law. So like Hooke's law, we have Newton's law. What does it say? We used to have a stress versus a strain. So I draw here, just for comparison, we had linear elastic material, a stress versus a strain, and then it was linear, and this slope is G, exactly, shear modulus. Newton's law, Newtonian physics, stress is proportional to the rate of a strain. So that is rate of change of a strain. How much is a strain changing over time? In 1 second, how much is changing? So it's different. And Newtonian fluids, they show a linear relationship. There is a linear relationship between a stress and rate of a strain. And this dot on top of gamma is like derivative with respect to time. So derivative just means the slope at any point. So derivative is respect. And the slope, this parameter here, is called viscosity. So now we have a model for viscous materials. It says that a stress is proportional to a strain rate linearly. The slope is called viscosity. It's a parameter we call F. What's the unit of viscosity? What's the unit? I thought today everyone is going to be energetic after what happened yesterday, last night. But I didn't count everyone who is tired. I don't watch football, I watch Super Bowl. So, unit. What's the unit of viscosity? Exactly. Radian is, if we don't count it exactly. In SI units? Exactly. It is like Pascal second. a little bit later. So, now we want to understand this a little bit better. We learned that, maybe it was too fast. So the unit is the unit of a stress times time. Gamma doesn't have a unit, so it would be the unit of a stress times time. So Pascal second, or it can be PSI second. A strange unit, but this is what it is. Now we have to also find a way. Before it was easy. We would say, okay, tau is equal to G gamma, so gamma is tau over G. Everything was easy. Now it's a little bit more involved. This is Newtonian fluid. We learned that stress is proportional to the rate of a strain. Now, if a stress is constant, then gamma will be increasing linearly with time. Right? So how do we know that? You can look at the rate of change of gamma over and see, okay, it is tau over eta. Now, if this is a constant, it means that if you plot gamma versus time, this will be the slope. So it is equivalent in a way when you say gamma is tau over G. It's similar, something similar to that, but we have here T. So here we are looking at how the strain is changing with time. It's increasing with a slope. Now, it becomes interesting. Now the next question is, what happens when we apply a constant stress to a viscous material? Before explaining this, let's just do for practice what I showed you before. Let's first consider this stress versus time on the top, and for yourself, draw a strain versus time if the material was linear elastic. I did it a few minutes ago, so try to forget about this graph for now. If it was linear elastic from that stress, how would you go to strain? And try to plot it. Just as we did before. So we apply constant stress at some time. First there is no stress. Then I apply stress tau, and then I take it away. I want to see if it was linear elastic, how would the strain versus time look like? If possible, try not to look back at what we did before. Try to undo it for yourself. If it was linear elastic, don't look at the graph in the mirror if possible. Let's just argue for yourself. If it was linear elastic, how strain versus time would look like. I know this is a new thing, time, bringing time into the equation. But this is a good. And I'm drawing it this way because it's good to align the time yourself that gamma, so it's gamma is tau over G. This is a linear elastic material model. Increasing the noise tells me that everyone has it. So if there is no stress, there will be no strain. In the beginning, 0. It's the moment you apply a stress, you will have a strain, and the amount of a strain you also know. It would be tau over G. As long as the stress is on, you have this strain, because that's your material model. The moment the stress goes away, since you have full recovery, because linear elastic, it goes back down to 0. So this is linear elastic. Instantaneous, full recovery, linear relationship. That's what it is. Now what happens when the material is viscous? Like here. So here, what we know is that the rate of a strain versus time, so the change of a strain is actually equal to tau over viscosity. If you have nothing in the beginning, 0, and you don't apply any stress, this will be 0. So 0 is 0. There is nothing here. Here is 0. You start from 0. So if you start from 0 and the rate is 0, it remains 0. Makes sense? So the rate is 0 actually. But since you start from 0 and nothing is changing, 0 will be 0. Now, what happens when I apply the stress? When you apply the stress and it is constant, with time, you are going to have a constant slope. This is what it says. It says the strain changes with time at a constant rate. That means it will be a line. Or you look at this equation. Gamma is a linear function of time. And the slope is tau over eta. Stress over viscosity. And it goes up to a point, which you can also calculate. So if, let's say, if I call this T0, this gamma would be tau eta T0. It depends on how long you are applying the force, in another way. If you apply 1 second, it would be different amount than if you apply 5 seconds. Here it didn't matter. It didn't matter. If you apply 5 seconds, it would be a speed tau over G. Here it matters. The maximum would be tau over eta, and then depending on how long you hold it, it continues. If I hold it longer, let's use another color. If I hold this longer, what happens? It keeps going. The moment I stop, what happens? The moment there is no more force, the rate of change will be 0. that doesn't mean that the strain is 0. That means whatever it was, it stays like that. It doesn't change. So to wherever you reach, you stay there. You don't go back. Because the rate of change is 0, not the strain itself. So that's why that at the end you see this horizontal line. Because that would mean that the rate of change of gamma with time is 0. So you see here, if I apply longer, if I keep the force on the girder in falling water, if I keep it for how many years it is? Let's say almost 90 years. If I keep it for 90 years, it keeps, the strain keeps accumulating. But if it was linear elastic material, it didn't matter. It would be still the same level of a strain. Does it make sense? Do you see now this time dependency? What it means? Any questions? This is important because the other material models, the building blocks are thin and it's like dashboard, the viscous material. So if you understand the string and understand the dashboard, then you can put them together to make complicated material models. Of course, concrete doesn't behave so simply. So there are more complicated material models, but this is one of the building blocks of that. Quick question, it's also very simple, just for you to write a few equations and warm up. So it's a piece of asphalt. I'm using asphalt because it's something which is very obviously stuff. And shear stress is 1 kilopascal. You actually don't need these dimensions. And you want to know what would be the shear strength after 5 seconds, given the viscosity. Just take a few seconds, stop here and there, look at the equation, try to write something down. Wow. If I had asked you like 10 seconds, it would be larger. So the point is something that I want you to remember and to mention is that in this type of material, everything depends on time. If you apply the same strength, if you keep it longer, you are going to get more information. Okay. I guess the solution is here if you have questions. So I want to finish the module 1 before we have the exam, and I don't think we can do that, and I don't want to rush through viscoelasticity because it's difficult. So I suggested the 16. A lot of people seem to have conflict. I could suggest 21st. That's the Wednesday after. But the problem is that week I'm on a conference, and I won't be personally here. I hope it'll be done by then. We probably won't be able to do it. If you did not keep out your big quiz,
Yeah, exactly.
if you look at the printed it, someone told me that, check, and I saw it So the dance starts, you have to be there.
Be there before. Be there. Be there at like.
Would you come in the morning class? Attend again?
No, we're concert.
All of you are done?
No, we were in the class all the time, but I was saying like.
How about Wednesday? Looks like after Tuesday.
I literally can't one day. Okay. Good. I just thought what you were going to say. Thanks, yeah, I'm excited.
46 hours?
Yeah, I'm excited. It starts at 6 p.m. on Friday and ends at 4
It
p.m. on
starts at
Sunday.
6 p.m. Is it, do you have to have a ticket before? You can just
Yeah, anyone can come spectate, but to like participate in the dance on the floor.
No, I would just want to come and see.
Oh, yeah, you can just walk in.
You walk into VJC anytime between like 6 p.m. on Friday and 4 p.m. on Sunday.
Great.
All right, thank you.
Thank you.
Sure.